So let me just, since we just started recording, we forgot to hit record at the very beginning, but so let me just quick go back through some of the things we were going over. The objectives here are just the basics of Python listed on this slide. These are the basics of functional programming, like numeric types, if-else conditions, the loops and functions, and the notes on these slides go over some of the things that that the target audience for this bootcamp is expected to already be familiar with, and these are the numeric types, the operations you typically give them. I wanted to highlight the distinction between true division versus floor division between Python and other languages, where if you need an integer division specifically, you have to use 2 slashes, whereas that is the default in other languages. And strings in Python are Unicode, so you can use special characters, and string concatenation or combining strings can be done with just a simple plus equals operator, like with numeric types. That's a very intuitive syntax to combine to both do string concatenation and numeric operations. And the note from this slide was that the print function in Python 3 requires parentheses, but does not in Python 2. And since Python 2 is deprecated, if you have not been putting parentheses on your print functions, you should get used to that. Then we briefly went over typecasting, which is the same as in other languages. You can convert between compatible types, and int and float casts proceed exactly as they do in other programming languages. You just call the type as if it were a function. And the caveat here is that casting from float to int does not round, it simply truncates everything after the decimal point. So you just take the integer that is immediately smaller than whatever float you are typecasting to an int. So I believe this was where we started recording. The import statements, if you're coming from C or C++, they look essentially like some version of pound include or using. If you're coming from the C-derived languages, you can specify specific functions or classes, whatever you are wanting to import, using this from import or import as, and you can manipulate the names of modules or objects you are importing directly within the import statements. So if in this example, PLT will refer to the pyplot module from within matplotlib. NP is an alias for the NumPy module. This third line, it's worth noting, it does not import the entire math library. You only take the log10 function, and I have reassigned its name to log. You don't have to do any of that. Like this fourth example just says like import sys, and if that's all you need, that's all you need. You don't need to complicate an import statement. The final point is this from blank import star construction. If you haven't seen that before, that's one thing that might be different from C or C++. This is more or less the equivalent of pound include. I code in C, not C++, so I can't confirm for if I were to say the same thing about using. I have not used that before, so I can't say one way or the other. But if you are coming from those languages, when you pound include some header file, you don't reference the functions by the header file. You just get the names of the functions themselves. That is the equivalent of this construction in Python. What this does is it gives you all of the contents of a package, and you don't have to specify. So you could say from math import star, and then you could just call sine, cosine, or log10 without saying math.sine or math.cosine. Moving forward now, we're getting into some of the array-like or iterable objects. that are found in Python, the first and simplest of which is a list, which is just a sequence of objects of any type, and they can be a mix of types as well. So lists are made with square brackets, and you separate elements by commas. So the example here just has the numbers 1, 2, and 3 with some string thrown in there, and you can index them using square brackets just like you initialize them. And as in other languages, the indices are 0-based. So the first element here is element 0 as opposed to element 1, and so on and so forth. And so the final element is always the length of the array minus 1. And one function that lists have, which is relatively nice, is an append function, which just sticks something onto the end. And you can also index lists from the back going in. So index -1 refers to the last element, which here would be appended. -2 would be 3, -3 would be string, and so on and so forth. So you don't need to do list indexing with some arithmetic using a known length of the array. You can just use, say, -1 or -2 and work backward from the end if need be. Right. Up next is the tuple object, which is very similar to a list, except you can't change it. A tuple is what we would call immutable, and that is just fancy speak for saying that you cannot change them. So when people say that tuples are not modifiable or tuples are immutable, they're really saying the same thing. I want to pivot just a moment and address a question that's in the chat. It says, what are the pros and cons of just writing import math instead of from math import log 10? So in general, it's up to you as the programmer. It's not any inherently better or worse to say import math versus from math import log 10. But in general, if you find that you're importing, that you've got a lot of from blank import blank statements, like if I'm importing a lot of functions from the math library by name, let's say not just log 10, but a bunch of other functions from the math library, it makes your code easier and a bit more readable to know that to know that you can just go import math and then you reference all of the functions from there. So it will reduce the line count of the code and make it also a little more readable. But that's the division between where you should go from using a from import statement to just a plain import statement is kind of up to you. There's another question that says, when would you use plus versus append to add something to the end of a list or tuple? So append, as I'll turn back to this slide for just a second, the tuple function at least is not compatible with the append function. So in this example, we have the same list as before, but now as a tuple. And I want to clarify here, you make a tuple with parentheses as opposed to square brackets like a list. But you can see here when I say example.append and I try to stick this string appended on the end, it throws an attribute error and says that tuple objects do not append objects. They don't have that functionality. Just like lists, however, you can index them from the end. And so if you were to stick something onto the end of a tuple, they are compatible with this plus equals operation. And so you can do that with a tuple. So if you want to stick something onto the end of a tuple and save it with the original tuple, you have to use plus equals as opposed to append. Whereas in a list, that is up to you. I think that they have the same functionality, so it's kind of whatever makes sense with your program and whatever would be the most readable. So I hope that answers the question. If there are other questions regarding what I've just talked about, feel free to throw them in the chat. So I think that covers everything for tuples. And we'll go on to the next iterable object, which is a set. And a set, you don't see a ton of these. They are much less common than lists and tuples. The primary advantage of a set is that they ensure uniqueness. So there are no duplicate elements in a set. So if you ever have a list of objects and you want to eliminate redundancies and ensure that every element is not the same as any other element, you can cast to a set and then back to a list or a tuple, and this will eliminate all duplicates. And that's what this example is shown here. I have X, which is some list, which is just the numbers 0 through 9, and I modify one of the elements to be the same as another. So I take element 0, 1, 2, 3, and I switch it from a 3 to a 4. Then when I cast to a set and back to a list, I only have one 4 in here as opposed to 2. So that is the advantage of sets. Other than this, you don't see a ton of usage of sets, but nonetheless, they have some useful functionalities like intersection and union. That's noted on the slide here, which you can do with the vertical bar and the ampersand sign. So if you find yourself wanting functionalities like this, it's worth knowing that you can do them with sets. But that said, you will not see them as much, and it's likely that you will not use them as much as lists or tuples. A quick function in the chat is whether or not this is the same functionality as numpy.unique. I believe so. In my, I'm going to look this up in a browser window quick just to see what the function is. And that sounds right. Fine. So it says find the unique elements of an array. That sounds like they are having the same functionality. So if you are wanting to find unique elements of some array-like object, some list, set, numpy array, whatever you may have, you can do that with numpy unique. You can also do this with set. Moving forward, the next iterable object or mapping object is a dictionary. So if you have experience in, say, C, C++, Java, there is a version of things like a dictionary in other languages, except they're usually referred to as hash tables or hash maps, some derivative thereof. So if that word or that phrase means anything to you, the dictionary is the Python equivalent. And I think this nomenclature of referring to hash tables and hash maps as dictionaries is starting to bleed into other languages as well. Some developers that are not as Python oriented but work with other languages are starting to pick up this nomenclature. Hashes are somewhat outside the scope of this bootcamp, but the bottom line for dictionaries are just that you can use them to map objects to other objects, regardless of what the objects you are mapping from and to are. You create dictionaries with curly braces. It is worth noting. I'm going to go back to the previous slide just a second to let you know that sets, you also create them with curly braces. The distinction is if you want to create a list with curly braces, you have to give it elements at the beginning or just simply cast some list to a set. If I just say X equals left curly brace, right curly brace, what you get is an empty dictionary as opposed to an empty set. So just be aware of that. The nice thing about dictionaries is you can kind of use them to give different lists or arrays or whatever you may have relatively intuitive labels and store them all in one place. Like this is what I'm kind of highlighting here with this example is I can say I have example is some dictionary, and I assign the string mass to map onto some list. And that is very useful in scientific code. It makes your code very readable and very intuitive to expand upon because you can give things in very straightforward labels. So you can imagine maybe a dictionary holding data on stars, and that data may be mass, ages, radii, luminosity, anything like that, log G. You can give all of those labels that you would normally attach to in just scientific writing as a string to your dictionary and write really concise code. One function that is worth remembering for dictionaries is keys, which just returns all of the pieces of the dictionary that can be used to map. Here, it's like this dictionary was originally A mapping to 1, B to 2, and 3 to C. And so example.keys, calling it gives you A, B, and 3, which you can use to pull the values out of the dictionary. Let's see, the next slides start getting into arrays. So the next piece before we get into say lists versus arrays is this is just kind of a nice flow chart, more or less, of which data type you should use for a given problem. And the basics of this is that it is always up to you as the programmer in which data type you use, but there are good choices and things which can be very useful. So if you want a logical key value connection, like say mass mapping onto a list or some array, then you should use a dictionary. And just to address a question in the chat, indeed, numbered indexing is not used for dictionaries. You should use keys. A good way to think of this is that a list is like a specific case of dictionary. If you have a dictionary whose keys are integers, then that is essentially the same as a list. Like if I have a dictionary where the keys are 0, 1, 2, 3, and so on up to some number of elements, then that's the same functionality as a list. Whereas dictionaries, they really shine in allowing you to map, say, integers, numbers, strings to other objects. That's the real difference between lists and dictionaries. So just to reiterate, if you want some logical connection, then you should use a dictionary. If you want to ensure uniqueness, a set is recommended. If it's an object that should never change, you should use a tuple. And if you answered no to all of those, then a list would suffice. So would a NumPy array. That is, if all you need is some iterable object and none of these questions answered yes, then the list or the array will suffice just fine. And if I am going to address a quick comment, is I agree with the comment in the chat. I would need to verify, but also if I remember correctly, Python doesn't store dictionary entries in any particular order. It uses the hash of the key to find the mapped object, so the order doesn't really matter. Like I said, hashes are a little outside the scope of this bootcamp, but if you know what hashes are and you have used them before, that may lend some insight to you on what's really going on under the hood. So the next thing we're to discuss is arrays, and this is something which is a major point of confusion to people when they're first learning Python. Arrays are different from lists. In practice, they're the same. They can hold the same amount of the same data, the same amount of data. The exact same things you give to a list can go to an array. The only advantage is that arrays have a specific implementation of data types under the hood, and that can sometimes speed things up. And in practice, it seems like it is often new information to people that the Python standard library does have an array object. You can just go import array in Python and you will find the standard library array module. However, the vast majority of the time, when someone says array, they're actually referring to the NumPy array. Pretty much all arrays you will run into, especially in scientific code, are going to be NumPy arrays. And you might guess, based on the font size, the boldface, italic, underlined, not, the most important thing to take away from this slide is that lists and arrays, even though they can hold the same data, they are not the same thing. And this is such a major point of confusion to really anyone who is new to Python, that I am going to stop and wait for people to parrot it back to me in the chat, or pop into the voice channel now and just say that lists and arrays are not the same thing. So let's hear you, everyone say it, or read everyone saying it. There we go. Keep them coming. Awesome. Yay. Awesome. I think it's sunk in by now. Feel free to send another one in the chat just to push the point. This is something which we'll come back to a little bit next week when we talk about object-oriented programming, because the basic statement that you can make about lists versus arrays is just they're different objects. But if you have never written a class and you haven't done object-oriented programming before, that may not mean a lot to you now, but once we've gone through some object-oriented programming next week, I'll bring this back up, and it will hopefully lend some more insight into why you may have found different behavior between lists and arrays in the past. So just to exemplify what can go on between lists and arrays is that the NumPy array allows multiplication with another array. A list does not. So here we have just some example code. I opened up, this is called a program called IPython. I will, for those of you who haven't ran this, I'll show you how to run it after we finish the slide. And I just imported NumPy, and I made X and Y is a list of the numbers 0 through 9, and Y is the array. So I can get the type of X, and it tells me that it's a list, and I can get the type of Y, and it tells me that it's this numpy.nd array. ND array stands for n-dimensional array. So you can have a NumPy array with however many axes you want. So what I am illustrating here is that, like I said, the NumPy array allows multiplication with another array. So I can say y asterisk y, and that does multiplication, and it does it component-wise. So if y is 0 through 9, then y times y is 0 through 9 squared, component-wise. So all of your squared integers. But if I try to do this with a list, it gives me an error. It says I can't multiply a non-int of type list. I can't multiply sequence by non-int of type list. So this is just one example of what could happen if you mix up lists with arrays. They have different operations. They have different behavior. And if you mix them up, you might find some confusing bugs, because you might find that you have a list where you thought you had an array, or an array where you thought you had a list. So general advice here is to pick one for a given program and stick with it. Work with either lists or arrays, and try to avoid allowing any lists to get converted to arrays, or arrays to get converted to lists. So this next caveat is that a lot of the code that you will see if you look at any of your collaborators' code, chances are it's using NumPy arrays. It's probably a safe bet to put money on the statement that a pretty large fraction of scientific code, not just in astronomy, but also other areas of physics, math, chemistry, biology, any other computational work that goes on in those fields, are probably using NumPy arrays. It's a very popular method of development. A useful feature for arrays, which this works for arrays as well as lists. I'm using the list as the example, but this same functionality does extend to arrays, and that is slicing. That you can use slicing to accept two indices and take everything from the first to the second index. So to quick address a question going back to the array business, a question in the chat says, are arrays only in NumPy? There is a built-in standard library Python array. If you launch Python or IPython in a terminal and you just run import array, that is the built-in standard library array distribution. But like I said, it is not nearly as popular as NumPy's array. The NumPy array object is definitely the more common one. So, to do a slice, you take two indices and you separate them with a colon. Very straightforward. And as the last bullet point would suggest, you don't have to give both of them. If the start or end index is going to be the beginning or the end of the array, you can just leave it off. So like here I have the list 0 through 9, and I take 1 colon, I get the first element all the way to the end, or colon -1, I get the beginning all the way up to, but not including the last element. So it's worth noting that with a slice, you get the element. Let's take this 2, 5 as an example. You get x, the second element of x, but you do not get the fifth element of x. So a mnemonic for remembering this is that the difference between these two indices, like 5 minus 2 is 3, you have a 3-element list, and 9 minus 3 is 6, you have a 6-element list. So the difference in the indices tells you how many elements you're going to get out of the slice. So the next set of slides starts getting into conditions. So if I'll take a minute and pause 5 or 10 seconds or so. If there are any questions on arrays, lists, tuples, sets, anything, slicing, anything we've covered so far, feel free to speak up or drop a question in the chat. We'll take 10 seconds or so and let you ask.
With slicing, I remember there's a way to do like every other one or something, but I don't know how to actually do it because it's been like 2 years. Could you remind us?
Right, there's a way to specify a step size. Yes, there's an answer was just popped in the chat. If you're going to give two, you can give the original 2 indices, and then another one separated by a subsequent colon tells you how to go through that. There is another way to do this. If you are going to not take a slice, then what you can do. So it's correct that yes, the indices do start at 0. So you can say this argument, which I'm about to drop in the chat, is the same as this one. So you can say x0 colon 5 colon 2. That's the same as just saying x colon 5 colon 2 because the 0 is implicit. If you don't need to slice and you just want to go through the list or whatever, the array-like object with some step size, you can specify 2 colons. So x colon colon 2, if I remember correctly, that goes through the list with every other element. This also, a useful construction is with a -1. So x double colon -1 reverses a list or an array object. And basically, the reason you use a double colon is because, like I said, you would have the start and end are by default 0 and just the end of the array. So if you don't specify them, then the 2 colons that would have separated those indices just become sandwiched right at the beginning of your index. Are there any more questions? We'll do another 10-second pause or so. Going once, going twice. All right, well, without further ado then, let's go ahead and move on. So that covers built-in data types. So we've discussed numbers and lists, dictionaries. The NumPy array also came up. That's somewhat inevitable when you start talking about lists and arrays. The remainder of this set of slides is on some of the constructions that you have with conditions and loops and functions. So conditions are if-else statements, and these statements are always binary, so they're always true or false, one or the other. There's no maybes with any of this. And one thing to know, if you are a pure Python programmer and you haven't had experience in, say, C or C++, is that numbers can be used as true and false as well. So anything non-zero is true. So you can just say if 1 or if 2, and that's the same as going if true. And so if you have numbers, if you're just going to say like if x equals 0, you could also say if not x, or if you're just wanting to say to check if x is non-zero, rather than just saying if x does not equal 0, you can just say if x. It will simplify some of your if condition. So in this example, I've got some block of if, elif, and else statements, which I've just ran a few times in succession, showing that this is just, it says if x is greater than 0, print x is positive. And like I said, I have here if x equals 0, I could replace this with elif not x. Then that would be the same as saying elif x equals 0. However, it's worth considering readability. If you're specifically comparing numbers, sometimes it's worth using this construction. It's also quite readable, and if you come back to it in like a month, you can very easily know what's going on. So this just prints, I have x equals 1, it prints x is positive, and this is very intuitive. I just switch the value, rerun it, it prints 0, and then same at the bottom. A caveat for these types of conditions is that only one will execute. So I'll toggle back and forth between these slides just barely. So note the difference is in this first condition, where I've switched the greater than to a greater than or equal to 0. And now, rather than this second block printing x is 0 as it did before, I swap this to a greater than or equal to, and it prints x is positive. This second block, it says elif x equals 0. That would evaluate to true, but this first block already evaluated to true, and it executed this first print statement. And because only one of these will ever run, it then just exits the if-else block entirely and skips this condition. So that's if you If you are less experienced with conditions, that is one thing to keep in mind, is that only one of these is going to go. If I needed both of these to iterate, if I wanted both statements to print, I would have to switch elif equals 0 for just a new if block. So it would be if x greater than 0, print x is positive. And then that if else block is done, and I have another one that says if x equals 0, print x is 0. So if you need more than one if condition to run, you have to make multiple if else blocks, and that is true in any language. You will always need multiple if else blocks if you want that functionality in C as well. So we are a few minutes short of the hour, but this is right at the end of conditions versus loops. There's one quick question in the chat, and it is, if you have more than 3 conditions, can you have more than one elif statement? Yes, you can have an arbitrary number of elif statements. So you can have if, elif, 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 elif for however long you want, and then a final else at the end. And you don't even need else at the very end. It's considered that if you have a relatively long if elif block, it's considered good practice to always put an else at the end, so that it is very clear in your code and very readable when the end of the block is. If there are no other questions, I'll stop for 10 seconds or so and wait for questions in the chat for people to speak up. But if we're good on what we've covered so far, I would propose we take our 5-minute break and reconvene in a few minutes to then talk about loops, for loops, while loops. So the question is, can you use list comprehensions for NumPy arrays? You can. If you are wanting to create an array out of a list comprehension, you just take, to create a NumPy array, you would just say numpy.array and then give it some list. And that list that you give it can be initialized in a list comprehension inside that block. So something like what I'll put in the chat, say np.array, something like, I'll just say I squared for I in range 10. This construction would give you a NumPy array of 0, 1, 4, 9, etc. up to 81. So you can put list comprehensions in there as well. If that doesn't answer your question, at least that was my read of your question. If I misinterpreted it, just continue. Okay, good. So the question is there a Python equivalent of the C++ switch statement? There is a switch statement in C, so I can answer that as well. I use switch in C a fair amount. I do not believe there is an equivalent for switch in Python, so you would be left with an if-else ladder. One thing that you can do, however, if you have, say, the one nice construction that I've used in Python before is using a dictionary to map keys onto functions, and then I can use a key to pull some function out of a dictionary and then call that. So that is, if you want to avoid a long if-else ladder, you can put functions in a dictionary and then use some key. So it looks like our participant count went up by 1 in the past couple of minutes. So if you joined, I'll just reiterate, we covered some of the built-in data types, just int and float, basically the numbers that you'll work with in Python, typecasting between them. And then we talked about lists, tuples, sets, dictionaries, and the difference between a list and an array. We then finished with if, elif, else conditions. Some of the questions we had on that were if you could have as many elif statements as you want. That is true. You can have an arbitrary number of elif statements. You can use list comprehensions within NumPy arrays. So you can say numpy.array and then give it some list comprehension to create your array. And another question we had was that there was a Python equivalent of a case switch type construction, as in C or C++. And the answer to that was there is no Python equivalent, but you can emulate that functionality by using a dictionary to map keys onto functions. And then you can give some key to the dictionary, get the function out, and you can call it. And you can bypass the computational overhead of evaluating all of the if conditions by using that construction. And that's the advantage of the switch and case constructions in C or C++, is there's less overhead. You don't evaluate those if conditions all in succession. And a dictionary mapped onto functions can give you that functionality. So the remainder of these sets of slides are about loops and functions, and a little bit about exception handling and catching exceptions. So to start, loops come in two flavors, either for or while. And they all boil down to more or less the same concept, which is you want some block of code to iterate or repeat itself some number of times. A couple keywords that will be useful here is break and continue. So if you are in a for loop and Python runs a line which just says break, what it does is it exits the loop. Whether or not it is actually done, break statements just cut the loop right where it's at, and you exit. You can also force start the next iteration of the loop, regardless of the current state of your variables or the program, with the continue keyword. So break and continue can be useful to kind of micromanage when your loops restart and when they stop. So we'll start with for loops. Those of you that have seen list comprehensions with for loops before, this second example will look familiar. For loops in Python come in basically two flavors. While loops in general, like I said on the previous slide, they come in two types, for and while. But for loops themselves also come in two flavors in Python. They're often referred to, I don't think this is standard nomenclature, but they're often referred to as explicit versus implicit for loops. Implicit for loops are what you have probably seen before, which occur within a list comprehension. These are seen a lot in, they were seen a lot in 1221 when I was the TA. Since Don Turndrup, the professor for 1221, is also the professor for 350, I would assume that you would see a number of them in that class as well. The explicit for loop, however, is much more flexible than the implicit for loop. The reason being is with an implicit for loop, it has to occur within a list comprehension, whereas explicit for loops can repeat entire blocks of code, and you can even nest them within one another. So you can have for I in range 10. I could then, in this example, I could have another for loop built off of this one, which would iterate some number of times within another for loop. So in this example, I'm just kind of highlighting the usage of continue and break. So remember that range 10 is just the integers 0 through 9. Range is just a built-in function which will start at 0 and count up until you hit some endpoint. You can give it a start index if you want, but that's not the point of these slides. This is just saying I'm iterating over the list 0 through 9, and I'm saying if I equals 5, start the next iteration. If I equals 8, stop the loop. And otherwise, at the very end, print I squared. And it's worth clarifying too that this construction uses an if statement on one line that is valid in Python, and that is valid in other languages too. You can just say if colon and then what should happen if that is true, and you don't need an elif or an else on that. You can just use this one line construction, which is very concise. So what happens is it goes 0, 1, 2, 3, 4, then it hits I equals 5. This evaluates to true, and it force starts the next iteration. So it doesn't print I squared for I equals 5, and hence there's no 25 that is printed here. And then it goes 6, 7, it gets to 8, and then if I equals 8 evaluates to true, and it goes break, which stops the loop entirely. So after it prints I squared for I equals 7 and sticks 49 on the console, it stops entirely, and you don't have anything else printed. Even though 8 and 9 are elements of this list, the loop was forced to stop when I equals 8 with this break statement. So the general statement for for loops and when you should use them is when you know exactly how many times some block of code is going to iterate or should iterate. That you can still use a break condition. Like this is somewhat for example purposes. I knew that this loop was only going to iterate for 0 through 7. So in reality, if this were a Python program, I just wouldn't have this if I equals 8 break. I'd just run this for 0 through 7. But in general, you get the idea. If you have a block of code and you can either say, if you know, you don't have to know the number right off the top of your head, but you should be able to calculate how many times the loop is going to iterate. There's a question in the chat that says, is there a computation bonus for doing it implicitly versus explicitly, or is it just shorter to write? The answer is the latter. It's just shorter to write. It's worth noting that the implicit for loop, like I said, it does not exist in other languages. So people would often refer to this syntax as, quote, Pythonic. But list comprehensions and these constructions and these types of constructions are very popular. It's very common to write some function. We'll talk about def statements soon and how you can call them and use functions in Python. But the idea is that you could imagine this list or this type of construction with a function where you say call some function for some number I for I in and then some list, and then you can map a function across an array in that manner. So next up, actually, rather than moving on to while loops, I'll just take another 10 seconds or so and pause for some questions on for loops before we talk about while loops. All right. Going once, going twice. We will go ahead and move on then to while loops. So in contrast to for loops, I just said that you should use a for loop when you know how many times a loop is going to iterate. For a while loop, you could probably guess then you should use them when you don't know how many times it's going to repeat. So in this example, what I've done is I've imported NumPy and I've aliased it to NP. And then what I've done is I've called np.random.normal. And what this function does is it samples a random number from a Gaussian distribution with mean 0 and standard deviation 1. So it draws bell curves centered on 0. And you can see what I got is some number minus 1.23. So what I do then is, okay, I say while x is less than 0, print its value and reassign it to some random number drawn from that same Gaussian. I don't know how many times this is going to iterate, specifically because x is a randomly generated number. And lo and behold, I ran this code. It went twice. It printed its current value. It reseeded x once. It got minus 0.9, and it printed that. But then once it reseeded again, it apparently got something right around 0.6. And there's no way of knowing that without actually running the code. So hence the usage of a while loop. To show this again, now x is positive. I just rerun the same block and say while x is greater than 0, print its value and resample from that distribution. And this time it printed 5 values. Okay, so this exemplifies what the types of constructions you should do. You should use while loops for, which is if you have something and you don't know how many times it's going to iterate, I recommend a while loop. And most software engineers, even from the ground all the way to the top, people who are most experienced software developers will say, yes, you should use a for loop when you know how many times it's going to go, and a while loop you don't. I want to call out one specific construction, which you will sometimes see in Python with while loops, and it has its place, but generally considered bad practice is this while true block of code and then some break statement. That is, it has, like I said, it has a place. You should generally avoid it, but it has a very important application. The reason it is considered bad practice is because if you're going to say while true and then have some if condition with a break, is you should just put that condition with the break as the while condition. Like in this block here, rather than just saying while true, x plus equals 1, if x greater than 10 break, I could just say while x less than or equal to 10, x plus equals 1. However, those differ in one very key aspect. And the very key aspect is that the body of the while loop will always execute once, at least once. So if you're coming from C or C++, this is probably reminiscent of what's called a do while loop, where you have a statement that says do, and then a block of code, and then your while condition at the very end. And do while is a construction that lets you execute a while loop, which you know will always go once. Python has no such construction. There is no do is not a keyword in Python. That is not that is not something that we have the liberty of in Python. However, you can emulate that with this while true break condition. So while this is considered bad practice, you should use it if you want this do while behavior. So just to add a little bit of an example to that, if I said here x equals say 12, it would come out the other side as 13, even though the condition is x greater than 10. That comes after the increment by 1. So that contrasts to whether if I had said while x less than or equal to 10, if x was equal to 12, it would stay as 12. It would not find that plus equals 1 argument, and it would stay where it's at. So if you need that construction, if you need that type of behavior where the while loop is guaranteed to go at least once, you should use a while true break construction. The next slide starts getting into functions. So I'll stop and pause for questions for a good 10 seconds or so. All right, going once, going twice. Let's dive in to functions. So functions are what you get when you use the def keyword. The def is powerful. It's worth noting that you can have def statements within def statements. So you can declare functions within functions in Python. That is usually not the same in other languages. Sometimes these are referred to methods. When I was first learning how to code, my first exposure to programming was with Java as an undergrad, and the professor referred to this technique as methods as opposed to functions. But that's just to point out that if you have a background in a different language, you may have heard a different term before. So the def keyword is followed by a function, or followed by the body of the function, which is indented once more than the function itself. So hence the white space along here. And that goes the same for the if statements and the loops before. Python, remember that Python uses white space as syntax. So the body of a for loop, the body of a while loop, the body of a function or a condition, it's always indented once relative to the declaration of the condition, loop, or function. So immediately after the def statement is where you would put what's called a docstring. If you haven't seen a docstring before, this is what they look like. We're going to be coming back to docstrings on Friday because what goes on in Python is that this is actually where you document your functions. And Python documentation, say like the NumPy library, has these docstrings on their functions, which are intended for you to be able to read and access. And we'll be going over how to access those on Friday. So it's worth noting that scientists in general and somewhat at large are notorious for poorly documenting their code, if they even do at all. And this is the butt of a lot of jokes. If anyone on here is a programming aficionado, there are subreddits called bad code or programming horror, and it's worth checking those pages out just to see the kinds of things that people who are really into programming kind of laugh at as bad practice, and the butt of a lot of jokes on with developers at large is just a very thin documentation, poor documentation, not commenting your code. So just general advice, if you are going to be building something substantially large, this goes even beyond whether or not you're going to release something publicly. Documenting your code is not just for other people, it is also for you. If you write some function, and I think it looks like this is exactly what Wayne is saying, is what I'm gonna be getting into now, is if you write a function in some file and then you come back to it 3 months from now and it is not commented at all, it's gonna take you a little while to figure out what it does. That's inevitable. You do yourself a favor if you write a docstring, and it doesn't even have to be this complicated. Even just saying calculate the value of x squared, that tells you a hell of a lot more than if you had just said def f of x, return x squared. Granted, that's a very readable function, and it's pretty easy to figure out what return x asterisk asterisk 2 is doing. But oftentimes functions aren't that simple. They usually aren't, actually. And Maria is echoing this in the chat right now. Definitely went back to some of her functions from 3350 and had no clue what they did. That is learning to document your code the hard way.
But there may be like a trivial reason why you might have two functions, that there's one compute x squared and there's another compute x squared, because they do it slightly differently or for a slightly different reason, that you needed something because of how it handled a certain variable or what you passed to it. And when you come back in 3 months, you don't remember why.
Yeah.
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 So it's just a good idea.
Yeah.
And camel case is my favorite.
Right. I'm sure that, so people hear all the time, oh, like why bother document? Why would I bother documenting my code? And sure, we've heard this. I'm sure that everyone has heard people say this. If you've been coding in Python or around astronomers or other scientists for any substantial amount of time, you've probably heard jokes about documenting or bad documentation, but you will never hurt yourself by documenting a little too much. It is an inherently true statement that the safe side, the erring on the safe side, is writing a little too much documentation, because you'll never look back at code you wrote and say, gee, I wish I didn't document this as much. So now back to functions and their actual use. Functions can do anything. The code inside this def statement, which is indented, could be anything, and it's obviously going to vary based on what the purpose of the function is. But documenting takes so much time, and also document units. These are things that are important. You can only shoot yourself in the foot when if you don't document units. You might try to give some function parsecs when it's expecting centimeters, and then you're going to come off many factors of 10 wrong. So that's worth that. Units are also something that you should note in your documentation. So because there's not much to say about functions at large, other than what the syntax is and how to work with them, because the body of the function is going to vary from function to function and based on what it does. So the one thing that is probably new to most, if not all of you, is the implicit return. So in C or C++, you declare the type of value that a function returns. In Python, you don't have to do that. And Python kind of skirts the need to have what would be called void functions and non-void functions to distinguish functions that either return nothing or do return something, by actually secretly having every function return something under the hood, whether or not you said to or not. The idea is that a function in Python will always return none if you don't have a return statement. So in this example, this would be a very shorthand documentation of the previous function, but I've modified it somewhat. Rather than saying return x squared, it prints x squared. So then the equivalent, Python, and this is for those of you who are new to Python, the comment character is pound. This function is being treated by the Python interpreter, the function which runs this code, is treating this function as if there is either a line here which just says return or says return none. Those are functionally the same. You can say, if you just say return, you're going to get return none, or you can explicitly specify return none. So then I call this function, I say, okay, x equals f of 2. It prints the value 4, like it should. And I don't have an error saying, I don't have a variable to assign to x, because this function returned a value of none. You can see I run x is none, and it spits out true. So if you, and I'm sure a number of you have done this before, but if you need to get a value out of a function, you need a return statement. The question is the return none like the void function C++? Yes and no. It is, so a void function in C or C++ will truly return nothing. Like it will not even return none. So that's a little different from Python. This is more like returning null. Like, so none in Python is essentially the same as null in C or C++ if you have experience in only one or the other language. If you want to return null from a C or C++ function, you have to give it some type, and it's usually a pointer type. But yes, it returns something. So the Python functions which don't return something are behaving more like they're returning null than nothing. If there are other questions on that, feel free to drop them in the chat. The final note about functions is variable scope. If you haven't heard about variable scope before, and Maria's question in the chat just now is kind of in this realm a little bit. Can you access a variable from inside a function if you put global in front of it? The keyword global does exactly what the name would suggest, is it makes a variable global. It changes the scope from local to the function to global for the whole file. So variables that you declare inside of a function can't be accessed outside the function. But as Maria's question would suggest, if you say global x inside some function, then its scope is no longer just that function, and it is global and can be accessed from anywhere in that file. The functions which, let's see. Yes, that is, so there's another comment in the chat says, trying to access a global variable before the def is created throws an error, and that is a true statement, but it goes one step further. I believe, and I'm not 100% on this, so it will be worth double checking what I'm about to say, but I believe that the variable will not actually be global until the function is called, because the body of the function will not evaluate to create the global variable until you call the function. So if you declare a global variable in a file, I believe you need, or if you declare a global variable in a function, I believe you have to call it before you can access it from anywhere else. One final note on functions is that things can simplify a little bit if you have just a one-liner function. And Lambda is something not a ton of Python developers use a lot, but they can be useful. It's really just a one-line function, and you don't even need to assign them a name. Like here, I could have used a lambda within some list comprehension or else block. But the idea here is I've said f equals lambda x squared. It's just a simple one-line function, and then I call it f of 3, it gives me 9. F of 4, it gives me 16. Just like saying def f of x and return x squared. Or I can write some function g, and it takes in some variable x and calls a function on x dot split. Split is a function which is held by string objects and separates them by spaces. So I can then just say g of an example string, and it cuts it based on the spaces and gives me a list back out. So lambdas are useful. They can kind of you can use them to declare some short, simple operation and then call them within your code. The caveat is that by nature, because they are one-liners, they don't have any error handling or any documentation attached to them. So you should only use them when the body of the function is extremely simple. So any lambda that is worth documenting is better replaced by just a def with a one-line return statement. And you might find, especially in a lot of production level code, that publicly available code or code that is intended to eventually be made publicly available, you'll see a lot more def statements with doc strings and a one-line return than you will lambdas. That's definitely true. So next up, the slides start getting into catching exceptions and exception handling. So we'll take another 10 seconds or so and take some questions on functions or loops or anything we've covered so far, anything that may have come up. So.
Is anyone feeling just completely lost?
Yes, please. That's a good. If you're completely lost, speak up.
I did a lot of this in grad school, but having to reach all the way back to my C++ class back in 2001 is quite a stretch of my mind. So this is all good for me, but it is sort of reaching back into the shadowy depths.
Right. All right, well, going once, going twice. Well, it's at least so it at least seems like everyone is on the same page with us. So let's there's only a few slides left, and then we'll get into some of the exercises for today. So the remaining slides, we've got some bit on some useful built-in functions, but before we get into that, let's do some of this business on error handling. And the way you would do some of this with a try except block is with these keywords: big surprise, try, and except. So try except clauses, to my knowledge, are not present in other languages. I believe it is a Python specific construction. So what happens with a try except block is that the body of the try statement will first execute, and if an error occurs, it will look for an except block that fits that error, and if it doesn't find one, it will raise the error. So in this example, I've pulled in the math library, and what I'm doing is I'm trying to call the log10 function with a negative value. And remember that you can only take the log of a positive number. Log is -infinity for 0, and is not defined for negative numbers. So when I say m.log10 of -1, it throws an error originally. But what I've done here is I've put it in a try block and followed up that try block with except value error, and then inside which it just says print, I caught a value error. And then this subsequent except block says, okay, if I caught a different error, something other than value error, then it just prints, okay, I caught some other error, something else. And what you can see is that it says, I caught a value error. So the log10 function raises a value error when the number passed to it is either 0 or negative. So then rather than throwing an error, the print statement evaluated, and the error was not raised. The function, the Python code didn't stop at the exception because of this try except clause. So then what I can do is extend the example by calling log10 with a string instead of a number, in which case it doesn't raise a value error, it raises a type error, and it says, hey, I expected a number and you gave me a string. So it says, okay, is that, try this. Some type error comes up. So it has type error. It looks at except value error, It says, okay, I don't have a value error, I have a type error. It looks at this next one and it just says except. Okay, everything else that wasn't a value error then will go through and execute this final except block. So then it prints caught some different error as opposed to caught the value error from before. And just like if else, you can have try except value error and some block, except type error and some block, except da 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 da, and you can keep going if you want to. Question in the chat says, should the general except clause always come after the specified exception? Yes, it should. So I don't know off the top of my head if I were to flip except with except value error, if I were to say put this second except block ahead of this first one, I don't know off the top of my head that would if it would find the first or the second one here, but nonetheless, the general convention, at least, is to put the general except block at the end. My intuition is that if I were to flip these, the generalized except block would always execute, and that's because Python being an interpreted language, this one is read by the interpreter and is found first. Good question. And yes, so like I said, you can specify different types of exceptions. In general, it is considered good practice to specify the error that calling a function might throw. Like if I'm going to say try m.log10x, I should say except value error as opposed to just a generalized except. The reason being that if something other than the error you were expecting comes up, it gets raised. You want that error to get raised if it is not what you were expecting. Except blocks. At the very end of an except block, you can add one other piece, which is a finally block. So a finally block, you should put something there if you want it to always run. Anything that is inside of a finally block will always run regardless of what happened in the try except clause. So, one example of that, which you may which a number of you will, which most of you will probably not run into, but is seen a lot in codes like NumPy or my own Python package. If you are calling routines in C or C++, where you can micromanage the memory, often the finally block will have code which calls functions to free up memory, so that if an error occurs, the error gets raised, but then the finally block will go in and free up any memory. So there's a comment in the chat, tested out my intuition from earlier. Apparently, if you give the general except clause first, Python won't run it. So not only does it need to be last for interpretation reasons, Python will throw syntax error by the sound of it if you flip them. So one thing to be wary of with a finally block is that if you have return statements in your try except block, the finally block and the return statement in the finally block will override any other return statements. So if I have, say, try return some value and it fails, and then an except block with other return values, or a finally block with some return value, it actually doesn't matter if what fails in the try block fails. If I have, say, try return 1, finally return 0, you will get a 0 from that every time. The finally block overrides return statements that have previously occurred. So that is the end of error handling. Are there any other questions about try and except clauses? All right. There are, try and accept are not the only ways. I want to clarify that try and accept are not the only ways to catch errors. I will show some other examples in some of our exercises, but type comparison is possible with a very simple Python keyword, and you can check for types with if statements, and then raise type errors or value errors following if conditions. You can say, like, if x greater than 0, do this operation, else raise value error, x must be positive. Constructions like that will also conduct error handling. In general, the rule of thumb is that try except finally blocks should be used when you can't do error handling with if, elif, else blocks or some other construction. The reason being that those are error handling constructions that are portable to other languages. Like you can use if, elif, and else to handle errors and catch exceptions in C, in C++, Java, JavaScript, other code as well. And so it's easily translated into other languages. Whereas try, except finally, it's not only pretty Python specific, but sometimes try blocks can get relatively slow. And that's because there's a good amount of computational overhead that goes on under the hood when you have this type of construction. So general piece of advice, error handling is best done with if, elif, and else, but try and accept blocks and finally blocks are always there should you need them. So the final slide is just a few built-in functions. These are useful and worth keeping in mind if you ever need some of this type of functionality. So any is a built-in function which will iterate over a list or an array or some iterable object and tell you if at least one of the elements is true. That's fairly analogous to the all function. You might be able to guess, given the names, that while any will tell you if at least one of them is true, all tells you if they are all true. So if every single element of some list or array evaluates to true, then all will return true. But if one of them is false, it will return false, whereas any will return true. So a good way of thinking of these is any essentially iterates through through a list with an or operation. So like the 0th element or the first element or the second element or the third element. And that will always give you true if one of them is true. Whereas all goes through them with an and. So like the 0th element and the first element and the second element and so on. And which will only give you true if all of them are. So, and that's essentially exactly what those functions do under the hood, is just iterate through with or and operations. Zip is a function which it's kind of a clever, cutesy name, but it takes a couple lists or arrays, any number of them, and puts them together component-wise. So if I have, say, the numbers 1 through 10 and the numbers 11 through 20, and I say zip my first array with my second array, just as arguments, so like zip array 1, comma array 2, and those are, like I said, 1 through 10, 11 through 20. The elements of the resultant will be 1, 11, 2, 12, 3, 13, 4, 14, and so on. So that's how you combine two arrays or array-like objects component-wise. Map is a function which iterates over an array of values and evaluates a function. So I could say map lambda x squared over range 10, and what that would do is it would say, lambda being a one-line function, which is here returning x squared. And if I give it range 10, that's the numbers 0 through 9, then what the map function with those two parameters will give you is 0, 1, 4, 9, 16, 25, and so on. So that's a way to just give a function which is maybe expecting one argument and have it evaluate an entire list or evaluate over all elements of some array in just one line. Filter is, as the name would suggest, takes in some array and takes out all of the elements which don't meet some criteria. So you could say filter based on, say it has to take in a function and a list. So you could say filter lambda x greater than 0 over some list, and that will eliminate anything that is non-positive. So the filter function can be used to preferentially remove elements of a list. Then min and max are precisely the same as in other languages. You get minimum and maximum values for some set of numbers. It's worth noting that min and max, you can give them lists or arrays. You can give them, I think you can give them tuples as well. You can give them some array, and they will operate and find the minimum or maximum value of an array. Or you can just pass them a bunch of parameters. You could just say min, and then just pass a bunch of arguments separated by commas, and they will determine the minimum and maximum of all of those values. A final note on some of these built-in functions is that zip, map, and filter all return kind of a special type of object. And if you want them as a list or a tuple or whatever, you have to cast them back to one, just with a simple typecast argument. So, and this is also true of range. So like range returns a range object, filter gives you a filter object, map and zip, same thing. And if you want them as a list, you have to say like list range 10 or list filter and some list, or list map and some function on a list. So just a point of clarification there, where if you're running some code and you run filter and don't see something particularly enlightening that comes out, that does have to be typecast after it is called. It's important to note here as well that map and filter were actually almost removed from Python between Python 2 and 3. So if you find yourself using these functions a lot, they may get removed from Python in the future. The reason being that the Python developer base tends to favor list comprehensions over these constructions. Map and filter and zip as well. You can really solve all of these functions, or you can really get the same functionality as all of them, just with list comprehensions and implicit for loops, things like that. So if that is the end of the slides, so we'll stop for questions on anything, anything that we covered in this set of slides, and then we'll pivot to exercises for about an hour before we call it a day. So, questions? Anything? Drop in the chat. Speak up. Whatever you got. Let's hear them. All right. I agree with Wayne in the chat. Y'all are doing awesome. Thanks for bearing with us for a couple long hours of review. So we didn't get any questions. I'll say going once, going twice. Right, the Git update, yes. Awesome. Well, let's call it on the slides then. If there aren't any questions, so we'll go ahead and stop share here. And what I'm going to do now is walk you guys through just the very simple way of updating your a Git repository. And I did just remember I do actually have a few more slides, but just 4 or 5 that I do want to go over as well. But let's do the terminal thing first, since we've seen a lot of PowerPoint slides today. So let me just get my terminal to a location which is worth looking at. That I want. Okay. Okay. Is everyone seeing just a terminal window here? I'm getting a thumbs up from Wayne, so I'm going to assume we're good. Awesome. So there's a quick question in the chat. Is there a keyboard shortcut on Mac to open the terminal? So if you are on Mac, I will show you quick how to do a spotlight search. Hit Command and then the space bar. That will bring up a little, like a search box right in the middle of your screen, and you can just type terminal and hit enter, and it will launch the application. You can use Spotlight Search to launch anything. You can launch Chrome, whatever. You can open documents. It'll just search for through your entire computer for things that look like what you searched, and it will give you options as well. I use Spotlight Search all the time. So what we're looking at, pivoting back to the terminal that I am screen sharing with you guys. I'm going to run a PWD quick. This is just my home directory, my work, and then my teaching directory, and then OSU Astro Cert 2020. So this is the directory that I have put all these slides and exercises together in, and it's the directory that is in the Git repository. So if you want to update which I would recommend doing now, if you want to update your copy of everything that is in the Git repository, just launch your terminal and just use your cd command to get you into the directory that you downloaded it to. And then the command is very simple. You just run git space pull, and you hit enter. And mine's already up to date, but I think most of you, I did push a couple updates yesterday. So for a number of you, you should see some files updating. And it'll print some gibberish, and then it's done, and you've got the new copies. It's exactly that easy. So if there aren't questions on that, I'll pause for a minute and just echo one of the comments in the chat. It says the global variable says you do have to call the function for the global variable to be accessed. So in the iteration of the function, when Python actually defines the function, the variable will not be global. You do have to call it first. Yeah. So are there any questions on this process? Just getting to your directory and running the git pull command. Awesome. So if there aren't questions on that, let's power through the last few slides. I wanted to take you guys through some simple file I/O, file input output, both with and without NumPy. This is just, let's see, let me pull up the PowerPoint. These are just 6 slides counting the intro, counting the title slide, so not much enter presenter mode and then share the desktop. Okay. And are we seeing now the title slide? Chat window go. Okay. Awesome. Thank you. Okay. So so I wanted to go through this because, you know, for the most part, astronomers can get by with just NumPy gen from text, NumPy save text, but that has an asterisk on it, which we'll come to later. So it's worth seeing how to read and write to and from a file using just the standard library, because you can't, you know, while NumPy is great and powerful, you can't rely on it for everything, and it's worth knowing what to do when NumPy isn't going to do what you need. So we're just going to go through a quick program that will write a very simple output file, and then we're going to read it right back in, and then I'll just show how NumPy can simplify that a lot. So for an example output file, the problem is let's just write the integers 0 through 9 and their squares separated by tabs. This is a typo. It's supposed to be separated by tabs with each integer square pair on different lines. So this is the program, which we'll go through in a second, but then this is the output file. And I think Wayne put a few of these in the Teams chat. You can look at the top of a file just by running more and then the name of the file. And so this just prints the first number of lines, or first some number of lines of the file. And here it's a very short file, so it's just 00112439 416 and so forth. So to write this, you want to use a file object, which Python, you don't have to import anything from in order to do this in Python. Open is just a keyword, which, big surprise, opens a file, and it takes in as arguments the name of the file and either an R or a W for whether or not you are reading or writing. And I put this in a with construction because file IO is very conventionally done in this way. This is a particular form of Python syntax which was introduced way back, I think, with Python 2.5 or something was when it came out. But but in general, this is exactly the same as just saying f equals open example.txt in writing mode. So functionally it's the same, but I've shown it here because you'll see a lot of this construction specifically with file IO. So then what we do is f is now our file object, and what I'm doing is for I in range 10, so that's the numbers 0 through 9. What I do is I write the string I and then a tab character. Those of you that have ran C code before, the /t and /n are still tab and new line characters. And then I'm just writing I and I squared to the file separated by this tab and the new line character. And then once the for loop finishes, the tab decreases by 1, and I just say close the file, f.close. Very straightforward. And this is the output from these few lines. Are there any questions on how this example program runs? No? Looks good. Okay. So then the next question to tackle is, okay, what happens if I want to read this back in? I guess I have an extra slide in here just to, reading it back in is on the next slide. I just want to call out here. These are some format specifiers. If you are coming from C or C++, this percent style notation is pervasive throughout pretty much a lot of I think every language I've used. I don't know if it is universal, but it's think it's pretty much throughout most of software development. Most languages have an equivalent of this. %d is an integer, %f is a float, %e is some number with scientific notation, like 1 point dot 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 whatever e, and then some number denoting an exponent on 10. %s is a string. There's various forms of this, and there are also even other ways to format strings in Python with a completely different syntax. So I've just linked the Python documentation to this here, and you can find all kinds of ways to stick integers and strings, or integers, other strings into your strings, floats, what have you, so that then this f.write line simplifies a lot. Basically, it just becomes %d, some integer, a tab character, another integer, and then a new line. And then to stick I and I squared in there, you have a % sign, and then I and I squared in there in the order they should be, with separated by a comma. And to answer the guess in the chat, the alternative to the W argument is indeed R. That is how you read. That is how you open a file in read mode. And to echo, I just want to echo Wayne's comment as well. Number formatting does matter when you're printing and reading in files between programs. If you print out a file, or if you print out numbers to a file in a specific format, that will affect how they are read back in, because a file will be reading what you read out. So if you write out an integer a float to some precision, to say a certain number of decimals past the decimal point, the file which reads it in will only have that level of precision. So like if you say write out to 2 decimal places, the file which reads it back in will only get numbers to 2 decimal places. That's worth keeping in mind if you're writing to disk between files.
And it can come back in weird ways, like where you wrote it out, but maybe the number didn't actually fit within the format that you said, and so it prints like a star or a nan or some other odd format. And then when you think that everything's fine because there was no errors, then you can't read in your old your numbers, and you don't know why a completely different program is just crashing that your advisor wrote. And it's because it actually didn't print anything that you were expecting.
So I guess let's move on to reading a file back in now. Much in the vein of what we're talking about right now, is how to take this same file now and get it back into Python. So what I've done here is I've first created a list to hold the data in, and then I've opened it with the name of the file, and just as you guessed in the chat, there's an R here instead of a W, and that specifies that I'm opening it in read mode. And then I just assign it the name F again, and I say I start by reading in one line. So f.readLine gives you the first line, and then if I call it again, I get the second line. If I call it again, I get the third line, and so on and so forth. And what I've done is I just said, okay, while the line is not empty, and in theory, I as the programmer know how many lines there are here, but if I'm reading a file that may have some long number of lines, or maybe I don't know exactly how many lines are in it, then a while loop is good here. So I just say while the line is not blank, x.append, so add onto the end of my list this list comprehension int I for I in line.split. So let's break that apart. What this does is it takes the line which was read in as a string, splits it based on white space into a list, and then casts everything to an int. So it reads 0, 0, separated by a tab, splits based on that white space tab character, and I have zeros now as strings, and then I typecast to an int, and I get the first element here, 0, 0. Rinse and repeat. I get 1, 1, and then those pop up as numbers in my list, and so on and so forth. And then at the very end, at the end of the while loop, I have to reassign line to the next line in the file. And then eventually my while loop terminates because now line is blank. It didn't catch any characters. So that terminates, and then I just close the file and I print X, and sure enough, I've got this nice 2D list, which was the output of my file in the first place. And I've just got a note here at the bottom. Append is a bad idea when lists are large, and large is a relative term. The number I usually keep in the back of my mind is like 100,000. So if you're working with lists that are any more than 100,000 elements, don't append or come up with some alternative to append. It's okay to do it once or twice here and there, but if you're appending over and over again on a list which is already large, your code is going to run very slowly. The reason being, what happens under the hood is when you append onto a list of element n, if I understand the implementation correctly, it actually has to first destroy the n element list and recreate an n+1 element list. So there's a lot of moving parts to an append function, and there are easier ways to do that, but append is the slow one. So I would stick with other implementations than append. And if you know how long a list is going to be, you should initialize a list of just exactly that length, and then fill the elements so that you're not appending to the end. Some comments in the chats. Wayne is correct. There are other ways to read in enormous files. One way to do it, which is if you're going to read in a file independently of Anaconda, which is many, many lines, a good way to do it is to use some construction like this, which actually just counts the number of lines. Say line equals f.readLine, n equals 0, or n equals 1 rather, and then while line does not equal blank line, read the next one and increment the number by 1, and then you know how long your file is, and then you can close it again, reopen it, and then fill in some list, and not have to worry about append potentially slowing it down. But that said, NumPy can change things, or NumPy can make things easier for the majority of cases. The second example, you can replace that entire with block with just a NumPy call to gen from text. Obviously, because it's NumPy, it will return a NumPy array rather than a list. But that's just a caveat, and you can cast back to a list after getting the NumPy array. But the bottom line here is that this becomes much easier. You just say NumPy gen from text, and you get your 2D list or array right back out. The reason I wanted to go over this though is right at the second point on this slide is that NumPy gen from text assumes a square data file. In other words, it assumes that you have the same number of quantities on each line. And if you don't have that, you'll see a string of error messages or warning suppression messages. The important thing to realize is that at some point in your career, it's highly likely that you will at least once get data that is not square. There's one key example of that from my field is if you have a data file with chemical abundances in stars, there will be many more abundances recorded for very bright stars. But then as soon as you start looking at dimmer stars, some of the elements that are less abundant and thus have intrinsically weaker lines, they might not be able to get an abundance for that element, so they don't record a value. So not every star in your data file will have the same elemental ratios recorded. And so then those data files, you can't read them in with NumPy. You have to read them in yourself because the data isn't square. The data aren't square. So just to recap, for the most part, you won't need to do something like this, but it's worth knowing how to do it in the cases that you can't use NumPy. Any questions?